Good morning. My name is Sarah Hagee. I am the Executive Director here for those that don't know me with the Electrical Association of Philadelphia. I'm joined by my colleagues, both Mir Malfara and Matt Dybert. And of course, joining me is Bob Maroney with Pillar Power Systems and our sponsor, Scott Stilley of eSite Systems. Before I turn it over to Scott, I just want to go through a couple of housekeeping items. As you've probably seen, your mics and your cameras have been turned off because, of course, we're recording this session. You are welcome and encouraged to submit questions. Scott is going to be monitoring the chat, so he's going to be able to answer questions in real time. But of course, we'll leave a few minutes towards the end if you'd like to submit questions as well via that chat. We will be sending out today's recording either later today or first thing tomorrow, and we'll include both Bob and Scott's contact information. So with that, Scott, I'll turn it over to you.
Thank you, Sarah. Welcome, everyone. I am Scott Stilley from eSite Systems. We're the manufacturer's rep for Pillar in the Philadelphia market. One comment that I just wanted to say that please, during the presentation, if you have questions, we're going to do questions at the end. I will monitor those and then I will read them all to Bob and then he can answer them. I'm excited for it. Bob Maroney is direct from the factory, very knowledgeable, and it should be a great presentation. I will turn it over to Bob at this point.
Great.
Thank you, Scott. Thank you, Sarah. Ladies and gentlemen, good morning. As Scott said, my name is Bob Maroney. I work for Pillar Power Systems. I'm the Northeast Regional Sales Manager for Pillar Power Systems, and I've been with the company for about 17 years. As Scott said, we'll take questions throughout on the chat. We'll address those at the end of the presentation. If I can't answer the questions, Scott will write them down for me, and we will respond in follow-up to your questions and get those back to you in the next day or so. But please do ask questions. So let's jump in, as we only have about 45 minutes this morning. And as Sarah said, we want to honor your schedule and allow you to get to work on time this morning. So, oops, a daisy, wake up. There we go. So, what will we be covering today? A short overview on Pillar Power Systems. We'll talk about mission-critical applications that Pillar participates in. We're going to have a longer discussion or an in-depth discussion on electrical topologies for UPS, their performance characteristics. We're going to talk about the product characteristics that Pillar UPS products carry. We'll talk about maintenance and downtime, reliability, sustainability, and then we'll conclude hopefully on time today. So let's jump right in. So Pillar Power Systems, founded in 1909, we're the present facility you see in the top right corner. We moved into in 1919, and we just actually celebrated here a little over a year ago, 100 years in that facility. Lower left corner, we also have a factory where we do all of our testing, and then our headquarters for the North America area is in Middletown, New York, just up north of Philadelphia. Pillar is actually considered to be one of the 5 top three-phase UPS manufacturers worldwide. We build most of our UPS products in Germany in a 500,000 square foot plant, as you see in the top right corner. We also have a 100,000 square foot plus plant in Austin, Texas. And we got about 6,500 employees worldwide. When we talk about applications, a lot of people wonder, where do you apply or use Pillar Power Systems UPS? Well, we're deployed in the gamut. We've actually been doing uninterruptible power supplies since the early 60s. You remember your early IBM mainframe computers? All those came with a Pillar standby UPS module. But we participate in hospitals doing imaging, in the data center, telecommunications, primary power. We do a lot of industrial work, chip fabs, pharmaceutical fabs. Like all UPS manufacturers, about 50% of our business is in the data center sector. And then we participate in a lot of these others, broadcast, gaming, transportation, airports, etc. So the equipment is used in a very wide spectrum globally for power quality, and power protection. So let's jump right into electrical topologies. This is probably why you checked in today, was to talk about this subject. So when you look at UPS topologies, there's really 2 things that we look at worldwide to see what people are doing for UPS. One includes mechanically coupled systems, where you have a utility connected to your UPS, and then the UPS's energy storage and backup components are connected physically to the UPS through a diesel genset, usually with a clutch, to an energy storage device into the UPS, thus connected to the critical power. Then you have electrically connected systems. which is more what you see in the United States. About 90% of the UPS in North America is electrically connected. So you have a utility with an automatic transfer switch, okay, that's connected to a genset for your long-term or alternate power. And then you have that connected to the UPS. And then you have the UPS has got a DC bus, which connects to an energy storage device, thus protecting your critical loads. So we're going to talk about them in mechanically coupled versus electrically coupled format today for the most part. So here's a little more detail on the mechanically coupled, okay? What you've seen historically in the United States is when you get into more of a, we call it a train. You have essentially a standby generator, clutch connected to your energy storage device is, then you go ahead and you connect into the UPS. So it's a long system, unified system. Generally very large capacity is you have to have a very, very fast start genset because those systems usually have just a few seconds of ride through time because they are physically connected. Is a lot of maintenance is not very flexible because it all has to be connected in one spot. So like the United States, a lot of people like to put the genset in one location, the UPS in another, and give them more flexibility in that kind of a deployment. They are available in not only low voltage, 480 volt, 600 volt, but they're also available in the medium voltage application, which is where you see them a lot as well. Then you see the more traditional electrically connected, or what we call static UPS, is what we see from a lot of the competitors in the United States using power electronics. Is they can be, connected through the energy storage is connected through a DC bus, okay, and you can have a multitude of energy storage in this kind of application. It can be chemical, batteries, lithium-ion, VRLA, flooded, or it can be kinetic energy or mechanical storage like a flywheel. Is generally these UPSs use a large amount of internally parallel components. We call these multi-module systems to get to somewhat larger sizes. As soon as you get above 500 kilowatts, they're usually using multiple modules to make a UPS module, okay? They're gonna have a lot of capacitors, a lot of fans for cooling those power electronics. And they're really confined to the low voltage area. So they're really available in 40 volts, and when you get really small down to the 208. As you get into larger systems, it presents the challenges of multi-module systems. That also, we believe, increases or decreases your reliability and increases your maintenance and downtime requirements. So when you look at the pillar rotary UPS, or what we call a uniblock, okay, is where electrically connected is for most part in the United States, okay, is you have genset, utility connected to an automatic transfer switch, is we have a DC bus between the energy storage and our UPS, and that can be battery, any battery you choose, or mechanical. We call it kinetic energy storage or flywheel energy system. But one of the benefits here is that we're not using capacitors and fans, and we're not using multi-modules. It's a single module system in total. It's also available in low voltage and medium voltage, so it takes us into a lot of different applications. And that allows us lower interventions and things like that. So let's talk a little bit about in more detail about the static versus the rotary connection system when you talk about that. Now, we have a little question here about how many people are familiar with pillar or rotary UPS. And we have a little pop-up screen, so if you kind of connect or click yes or no, how familiar you are with the differences between static and rotary UPS, that would be great. It'll help me identify how to move forward in the slide deck. So let's take a quick look here. That's a daisy. There we go.
Mr. coming in.
Talk about what a rotary machine really looks like and what it does. And first off, there's a true difference between rotary and energy storage. In fact, as it was noted by Frost and Sullivan, I think most eloquently stated by Frost and Sullivan, is basically in a rotary UPS, the load is fed directly from a synchronous generator or a motor generator, or more common load known as an MG. It's distinction between the static UPS and the rotary UPS doesn't lie in the energy storage, okay? It's the function of how the machine gives you protected power downstream. Is when you say a guy's got a flywheel energy storage system, that's not a rotary, that may or may not be a rotary UPS, is because it's all a function of how that stored energy is connected to the UPS. Rotary is a type of power protection. So we're going to talk about that and the differences now. All right, well, looks like we're about 50-50 crowd for people who really have heard or talked about the differences between the two. That's great. So static UPS is traditionally artificial sine wave generated with power electronics, thyristors, rectifiers, IGBTs. As technology has progressed over the years, they've gotten better at it, more efficient at it, provided better technologies. They're using digital signal processing, DSP, in conjunction with PWM to create average pulses that they can use on the output. And then they use a lot of capacitors to smooth out that waveform so that it's acceptable to the downstream loads. When you're using a lot of power electronics like this, especially as you get above 500 kilowatts, is you start to generate a tremendous amount of heat doing this conversion from AC to DC and back, and having to do multi-modules to get the capacity. Now you start to, what comes into play then is a lot of cooling fans. Between the capacitors and the cooling fans, we consider those to be single point failures and have impacts on reliability for the system. Oh, sorry, wrong one. There we go. So let's talk about how a rotary machine works a little bit. By using a rotary machine or a motor generator, okay, spinning mass, is we generate a natural sine wave, okay, through using that very large, robust motor generator system, okay? We don't have to parallel multiple power electronic or multiple power stages like a multi-module system to get to powers above 500 kilowatts. Okay, no smoothing capacitors in the system, no filters in the system. You only have one fan in the entire UPS system, and it's a mechanical fan. You'll see it in a minute where it's connected to the motor generator. You can also go to very, very large capacities in a single module system. So thus you have a lot more real-time uptime, lower maintenance intervals, and we believe a higher, more reliable system. And we'll show you that that's true later on in the presentation. So reactive power support. So static UPS, you use the IGBT inverters with an output filter to change the PWM to sinusoidal, okay? Essentially the capacitors are, again, that smoothing waveform, and they also work with lagging power factor. Is when you use a rotating machine, and we'll get into details of how it actually works, okay, there's no need for the waveform filters, for one. The generator provides reactive current to the system as needed based on excitation from the output of the system. This regulates voltage as seen by the load, okay? And this means that also the motor generators not only can supply or absorb reactive power based on the needs of the output power form. So how do we do that, and how has it matured over the years, okay? Well, in the old days, as in the large mechanically connected systems, you actually had a separate motor that was shaft connected or mechanically connected to a generator. And you needed those two components, one to motor to run, to spin that machine while it's online or on utility or having power divided to it. But it also needs to be able to generate current or reactive current for output to load for voltage regulation. 1980, Pillar came up with a hybrid machine and actually unified into a single system. You'll see it here in a minute. There's a picture there on the right. But it allows for a more compact, reliable, cost-effective system that allows for that power factor, voltage regulation, harmonic mitigation correction as we go through the system. Is another component to the UPS that we're going to talk about here for a moment is essentially our input-output choke. It's an isolation, high impedance, and connection choke, low impedance, that's connected to the motor generator. Now, the choke actually provides us a connection point to the critical path of the UPS. It allows us to inject or take VARs off of the critical path to hold output waveform to plus or minus 1% at all time, okay? It also provides true isolation input to output. For example, this choke would take a 50% current harmonic from your load and take it down to less than 3% on the input of the UPS. And as you know, current harmonics going back upstream to your utility or your infrastructure cause problems. And it also provides difficulties for power generation equipment, generator sets, to voltage regulate. If you have a high harmonic load that's being allowed to propagate back towards the generator set, it actually can keep the generator from being able to voltage regulate and come up to speed. As you'll also notice today that there's no filters on these systems because of this choke, okay? Also, the choke provides us fault contribution is only about 1%, 1.8x upstream, but it does allow, because of the low impedance component of it, up to 14 times fault contribution downstream to help clear faults when you have to clear those downstream breakers. So we're going to start is look at the next part here is going back to talking about the motor generator. The uniblock is what we call it. And this is our power conditioning component we've been talking about. Is, as we talked in the top right corner, you can see where we have the motor winding and the generator winding unified into the same stator. And then you have an excitation winding, and then we have a damper cage around the system, all surrounded by a stator. When you look on the left, this is what it would look like in total. Is starting at the top, you heard me mention earlier that we have a single fan, and the fan sits atop the uniblock motor generator. I'll show you a picture of the UPS a little later, but that single fan is a large fan that's connected to this big machine that pulls air in and cools the entire UPS system from energy storage to the DC bus to its own self here and its own power electronics to eject this out the system. Okay, we use a brushless bearing on the top. We have brushless excitation as well. Okay, then we have the motor generator windings, which we've been talking about in a unified rotor. Okay, then we come to a common 4-pole slip rotor. I apologize, I got those returned. Is the excitation of the stator above that we're talking about. Is vertical alignment, 2-bearing machine, and then we have a pony motor. Benefit of the pony motor, because this is a fairly substantial electric motor, is we don't have to oversize the input breaker system because the pony motor allows us to bring that up to speed very quickly without having to increase or overload that front bearing. So this gives you an idea of what this machine does and how it configures. When you would look at this inside the UPS, it would be about 2.5 feet in diameter and about 4.5 to 5 feet tall. So it's a large electric motor, stands vertically on bearings for reliability. So let's start to build a UPS with this system. So as you look at the top here, you can see we have our input and output, utility and load. We have a manually initiated automatic bypass, and then we have Q1 input breaker, and we talked about our choke. So we have our isolating choke, which is the high impedance choke, and then our coupling choke, which is our lower impedance choke, which allows us to provide isolation input to output. Is if I'm going to deliver VARs to the load because voltage is starting to fall, for example, and I want to buck it back to 480 nominal, plus or minus 1% per specification requirements, is that flow of those reactive current is going to flow to your load or through the coupling choke because it's a lower impedance, right? Okay. Is if we have voltage sags, the uniblock monitors those voltage sags. There we go. I was missing a part of my slide. I knew it was there. Is if we see voltage dip, we're going to monitor, see that, and what we're going to do is we're going to increase excitation of the uniblock to deliver reactive power to the coupling choke to the load to provide output waveform. If we see a spike, what we're going to do is we're actually going to reduce excitation, and we're going to absorb VARs into the uniblock motor generator to hold output power and waveform nominal. Okay, as I said, the choke provides bidirectional current and voltage harmonic isolation. It'll take a 50% current harmonic or load harmonics and mitigate those and give you that isolation you need. Okay, you'll also notice, as I mentioned earlier, there's no filters on the input to the system. We don't need them because that choke provides that kind of filtration. Any questions about that? We'll see those pop up early on. So now we've started to build this UPS. So we've got your utility connection, your choke with Q1, Q6 gives you that output isolation per code, is Q5 to be initiated in a manually initiated automatic bypass system in the failure mode. You'll also notice that there's no static bypass in this system. And if you look, the uniblock, as I said, can provide 14 times nominal current downstream to help clear downstream faults. In medium voltage, it does come down to around 6 to 8 times that level per the system. But one of the nice benefits is you don't have to deal with going to bypass when you have an instantaneous requirement for inrush on the system. And you'll see where we actually take advantage of that in some of the application notes in a few slides. So let's add energy storage to the component, because without energy storage, we don't have uninterruptible power for very long, do we? So in the pillar power systems our first choice is the power bridge or the flywheel energy storage device. And we use that is to provide energy buffer or ride through from an outage or an extended outage to get us to an alternative energy storage device. That could be another utility. It could be a generator, a multitude of alternative energy storage devices. We can give you those flywheel energy storage devices anywhere from 6 megajoules up to 60 megajoules, so that you have as much ride through and power as you need to make that transition. Okay, based on the topology of the system. You heard me talk about voltage regulation, harmonic mitigation, power factor correction of the UPS systems. But this is a parallel online architecture. So in the event of a frequency excursion, we're going to actually disconnect from the utility. We're going to go to the stored energy device, be it flywheel or batteries, and then we will correct back to the reference in the United States, 60 hertz frequency, and we can do that in anywhere from 1 to 5 hertz per second. That's an adjustable slew rate. You'll also notice we're using an SCR bidirectional converter bridge between the energy storage device and the uniblock. And we use this because the flywheel, like the batteries, operates at a different voltage than you're using on frequency. So our flywheels run about 785 volts AC, 1,000 hertz at full speed. Okay. You'll also notice that I comment here that the power bridge can run anywhere from 1,800 to 3,300 RPM. One of the benefits of a rotary UPS like this is we can do something that the static traditional guys have a hard time with. And that is we can actually use the flywheel to not only deliver instantaneous ride-through power, but in a microgrid application, I can actually dial the flywheel speed down to around 2,400 RPM if we want to. And I can actually use it as a shock absorber in a microgrid application. So think of this system as the utility to load as a microgrid bus. And you've got photovoltaics, wind generation running, and utilities serving power, and somebody shuts off a motor in the facility quickly. I can actually, because as you know, the microgrid equipment, photovoltaics and wind generation, don't start producing power immediately like the motor being shut off does. So I can absorb that excess generated power into the flywheel. Obviously, it speeds up a little bit, and I can hold that energy there until the microgrid bus stabilizes. And then as it stabilizes, I can slowly feed that stored energy in the flywheel back onto the microgrid bus as it stabilizes, bringing the flywheel energy storage device back to nominal speed. So nice benefit of having that ability to run the flywheel at multiple speeds is be able to take power in or out based on application of the output side of the UPS, which is not available to you in other applications. So it provides itself a lot of flexibility in a lot of applications. We've been doing these for a long time. So let's move on. One thing that you heard me allude to is we not only do mechanical energy storage, we do chemical energy storage. So we can do everything we've talked about with batteries, and we can do those with lithium ion, nickel, cadmium, VRLA, flooded jar. You tell us what kind of stored energy you want to use. It can be mechanical or chemical energy to do the same things. Okay, so let's start talking about performance characteristics, if we could. One of the benefits of a rotary UPS is its ability to provide a multitude of performance characteristics at a higher level of order than you would find traditionally today. So I picked off a few that I think people pay attention to the most. One is the input-output isolation of the system. Remember we talked about the choke providing that isolation. Here you can see the input voltage with a lot of harmonic notching in the system, okay, and a lot of transits on the system. Here, and then you can see the output waveform nice and clean, and that goes on for an extended period of time regardless. One of the benefits with the UPS is we don't go to discharge, or we don't go to flywheel or energy storage until a minimum of 15% deviation from nominal low, 10% high is, and until then we can do full correction to tolerance requirements, plus or minus 1% non-voltage, okay? Half a hertz off of 50 hertz, and that is adjustable, how sensitive your voltage and frequency are. We can adjust that tolerance from 1 to 15%, actually 20% low. We can go as low as 50% with support from the flywheel before we disconnect as well. But this gives you an idea of how we handle that isolation and what that waveform would look like on the output of the UPS. This is a nice transient system. The input voltage taking a spike on the transient, and you can see your output voltage waveform being very, very smooth. No transients carried through the system, giving your downstream critical loads the voltage that they require in a nice, clean waveform. This one's kind of nice. This shows an input failure of the energy storage from the utility. And as you can see, there's no visible voltage deviation as we transition from utility energy over to UPS energy. And we go into discharge, then making the transfer over to an alternative energy supply. Here's a harmonic mitigation slide. The top slide shows about a 50% current harmonic on the load side coming in. And then you can see on the bottom, your output voltage does not reflect any of that nice clean output voltage of the UPS to your loads to give your loads what they need there. That's probably showing about a 5% voltage deviation from that 50% current harmonic to the load. And then the input voltage and current, as you can see, the waveforms are nice and clean. And what's nice about that on the input, you'll see that there's no propagation of harmonics to the input voltage waveform that can have input on your infrastructure, whether it's your lighting in the building or sensitive equipment, or for that fact, your power generation that might not be able to get on the bus with high harmonic currents in today's economy. When we start, so let's take a look at where we apply some of these things. It's nice to know that people are actually buying and using this. For example, in this case, Global Foundries up in New York. Global Foundries is using about 12 of our systems. Is in that community, they would have their loads, a lot of motor loads, a lot of inductions, motor loads, is a lot of equipment loads, which can be very problematic. A lot of fans, pumps, motors, and then they also have, they're out in the middle of the state where the utility is somewhat problematic for them, especially when they have big storms come in off of the lake, the Great Lakes. They've been using this equipment since early 2011 and have been very happy with it. It's been a production system for them. And in that particular case, there's about 12 megawatts of load on the pillar rotary UPSs, providing that protection for them. The systems are run at about 75% of load, and all systems are under load at all times. And then if there were to be a failure of a system, they have redundancy built into the system as well. So another type of load or requirement for a lot of people, and that is getting into medical equipment loads, is high nominal to peak requirements. We talked about, remember that 14 times inrush current we can provide? Is when you put a rotary UPS in this capability, as you can see, we're going from 15 kVA, which would be about 12 kilowatts up to 100 kilowatts in sub-cycle transients. You don't want to be going to bypass or your energy storage on that. You want to be able to support those very, very fast spikes without having to make those transitions. You don't want to be going to bypass and having your imaging gear on utility during bypass because the UPS had a limitation on its ability to cover these kind of loads. Imaging and MRI equipment, so you'll see our stuff there a lot. So, next question. Do you know why a lot of the UPS guys avoid motor loads? Well, it's a similar answer to the one we just talked about for the MRI. Okay, when you take a look at a motor load, you have starting. Now, if you're on a VFD, you only have 2 to 3 times of nominal current for starting. But sometimes you need to handle a motor across the line, which, as we all know, depending upon the rating, can be as much as 7 times nominal current. And if you look at the inrush requirements to start motors, a static UPS do not like that. You'll deplete the DC bus going to stored energy and to bypass immediately. And you can do damage to those type of systems depending upon what kind of motor you're talking about. Again, with the large capacity and strength of the UPS of a rotary system with that large inrush current capability and that big motor generator and its ability to deal with heat internally without dozens of fans, it is much more well suited to, interesting that, thank you for your responses. It is, the motor is much more well suited for these type of robust requirements because its abilities to A, deliver inrush current, and 2, you have a lot of steel to dissipate that heat from that kind of rise in requirement. As you can show a motor here. Come on, there you go. Regeneron Manufacturing up in New York State. This is a fill plant for a pharmaceutical facility. Almost all motor drives in that facility. Many very large motors across the line starting in that particular application. So let's start looking at product characteristics. So when we talk about sizes that the UPS from pillars come in, they go from 675 kilowatts all the way up to 3,240 kilowatts, single module systems, okay? So you can do them in low voltage, 480 volt or 600 volt, and you do them in medium voltage. In medium voltage, you can do any voltage that you want to do. Is some of the other characteristics, very, very high efficiency, advanced control systems with self-diagnostics, which allows us much fewer interventions for starting. As we said, very, very large, compact footprints, high power density. Is you'll find that we're usually about half the space requirement of battery applications when you use our flywheels. Okay, wide dynamic operating range. We've been talking about applications in different types of energy storage, suitable for stabilization, microgrid, renewables, and things like that. Very sustainable. Is we use 100% recyclable steel. So, characteristics: decentralized control architecture. Okay, with no dedicated master controller. You have multiple controllers, so if any one component fails, we don't lose the entire system. We're using cable redundancy. We're getting rid of ribbon cables in our systems, CAN bus systems. Hardened printed board, printed circuit boards. So all the critical components are hardened within the UPS. How often have you seen a guy reach into a power electronics box and hook his sleeve on a printed circuit board and yank a cable out of it? Enhanced condition monitoring. So we know what the speed is of our MG, what the status of our MG is. We know exactly how much speed and stored energy is in that flywheel energy storage device. So we know exactly how much ride-through time we have to mitigate your power quality issues. Oops. Is a very, very detailed HMI that takes you from everywhere from the component temperatures, voltage, currents, power, to input, ambient humidity, speed of the flywheel, and the MGs, data loggers. We have a 3-level data logger that logs data 1 second, 1 minute, and 1 hour, and it holds the 1 second for an hour, and actually 3 hours, and it holds the 1 hour up to 18 months. So you have a true record of what the system is seeing. High level of communication. If your customer wants to, they can do email, web, Modbus, SNMP. How do you want to communicate and monitor your system? We also have an app, so people can actually seed their machines, as many as they want, from anywhere in the world and get notifications from the machines, not only to Pillar and to the home office, but it'll come to their iPhone or Android phones. So in conclusion on the characteristics, improved reliability through is more unified systems, higher communications capability, fewer internal communications connection points is a much more reliable system. Let's talk about maintenance and downtime on the 3 types of UPS systems we have out there. When you do mechanically connected UPS, big rotary machine, is over a period of 20 years, you're going to have over 15 critical maintenance systems. When you look at electrically coupled static UPS, likely 2 a year, okay, So, or at least one a year, you're going to have somewhere in the order of 10 as main maintenance intervals. With a pillar rotary UPS, you're only looking at 2, okay? So when you get to the bottom line, total days of downtime for maintenance on these 3 different type of UPS topologies, you can go from as high as 27 over that 20-year period to as low as just 2, is depending upon what your real maintenance events look like over the life of the systems. Is when you look at a pillar rotary system, is 2 is because we do is in a 20-year period where we have to do the bearing changes in the motor generator, and if it's a lithium ion solution, as this evaluation is, so we can compare everybody equally, is we're going to probably do a battery change at year 10, is depending upon what the battery technology the customer looks at is. But we try to maintain and reduce the number of events that your system have to come offline. Just another representation of the difference in offline periods or lack of offline periods during that period of time. Reliability, if you look at the pillar rotary UPS, is the ECR, electrically connected rotary UPS uniblock, has a substantially higher reliability rate. And this is based on real-time events over the life of the UPS, because pillar does almost all the work on all of our UPS, over 3 million hours of MTBF. If you look at traditional static UPS today, as they've gone to multi-module systems to achieve power, is because now instead of having one inverter section for a 750 kilowatt UPS, you might have 2 for that size. Or if you're going to a 1,000 kilowatt system, you might have 3 or 4 inverters. Is their MTBF has compressed and come down over the years for the clients, is making the systems have a higher failure rate compared to a single module rotary system. Wanted to kind of highlight some of the systems that we see when we look at them. This is a standard 1,000 kilowatt double conversion UPS at 1,200 kilowatt UPS out there. And I wanted to highlight some of the things that we start seeing as product count when you start looking at what it takes to make these systems. So what you can see here is they actually use 4 300 kilowatt modules to build a 1,200 kilowatt UPS, as highlighted in the red box. Okay. Not only that, they've got over 18 fans per each 300 kilowatt module. To get to 1,200 kilowatts, it's 72 fans. And any 2 fans can be a single point of failure for the 1,200 kilowatt UPS if you're using it at its design capacity. When you look at that type of a static UPS, you're looking at hundreds of capacitors in each one of those 300, hundreds of capacitors when you look at a 1,200 kilowatt UPS system. You have IGBTs to do your power electronics. Each 300 kilowatt system is going to have 3 input IGBTs and 3 output IGBTs for each of the 3 phases. Now you're getting up to as many as 24 discrete components inside of that UPS. In a 1,000 kilowatt system, you're looking at almost 70 components. Is when you look at internal breakers, isolation breakers, filters, IGBTs, output filters, static switches, bypass contactors. It all adds up. Is, as I said, in a 2,000 kilowatt system, you'd be looking at a count of over 140 components, not including capacitors and fans that we just talked about. So how does that relate? If you look at a pillar rotary UPS single module system, and this could be a 675, a 1,000, or 2,000, doesn't matter. You're looking at about 8 comparable components on the system. We feel that this is indicative of a reliability differential that you saw in my MTBF. Okay, and we're not even, in neither system did we count stored energy, be they batteries or flywheel. We're just talking about the architecture of the UPS. So, reliability summary. Proactive monitoring, we talked about capabilities in the system. Fewer or 0 offline maintenance over the term of the system. Fewer interventions that you have to tell your customers about. Lower maintenance costs, better TCO, okay? And in the new normal today with COVID-19 is most of the people we're talking to are telling us that they have fewer people on site to manage, monitor, and maintain their systems. So they need systems that are higher reliability with fewer interventions and need less work that they can bring, that they need to bring people online on property for. Sustainability is when you look at the system, the pillar systems, we use recyclable steel, which reduces carbon footprint. Executives today are looking at and much more sensitive to the carbon footprint requirements, and they will be doing so going forward. Many of our customers are get LEED certifications, Green IT, Carbon Trust certifications, using 100% recyclable components. They're leveraging these systems in their designs when they go to anywhere from to design to build to implementation. So summary and conclusion, Rotary, large-scale single module systems with less infrastructure, much lower downtime, okay? A wider, more flexible, more flexibility for the DC data center and industrial sectors for the clients, okay? More efficient, save energy, lower CapEx, is a choice of voltage systems. One of the nice things about this is we actually can do your voltage, whether it's 480 volt or 1247, 4160, 15 kV. It doesn't matter what your voltage is, we can accomplish that for you. So I think I've ended about on time. I hope I did not go over for you. If you have questions, please, I hope you shared them with Scott. I thank you very much for your time today. Feel free to reach out to us. Our contacts are available online. I'm going to hand it back over to Scott to close it out and kick me to the curb.
Thank you, Bob. That was a great presentation. There is a question. Does this equipment require conditioned environment, or can it be placed near the facility equipment in an electrical room? Good question. Go ahead, Bob.
Absolutely is. It really depends upon where you're going. I'll give an example. I'm working on a project in Nevada in the desert where our ambient temperatures can reach 120. So in that environment, we're going to air condition that environment for those really robust times. At the same time, up in Boston, Massachusetts, we did a project for Harvard University where we put it in an outdoor enclosure and we put it on the north side of the building. No air conditioning needed at all. It's very, very robust. So let us know, but 99% of the time with rotary machines, we're not dealing with sensitive IGBTs that need to be cooled all the time. Remember, no fans. And more often than not, we're using flywheels. So we're not having to maintain a battery room ambient temperature. So it's very, very robust. So 90% of the time, we don't need anything other than to be inside, non-condensing. Please don't put me out in the rain. Scott.
Yes, thank you. That was from Paul. Another question is noise an issue?
Absolutely not. The machine runs at about 74 dB at 0 feet, just like a regular UPS.
Very good. There was another comment, excellent presentation. Thank you, Bob. And they asked if we can share it with them. Just wanted to make a note, this is being recorded. We will certainly share the presentation in PDF, but after the presentation is completed, EAP will make it available, the whole recording.
Yeah. Also, if I may, my contact information is available. If you have a question, please feel free to contact Scott or myself directly, and we'll answer your questions and see if we can help you out that way as well.
Okay. Another question is day one cost versus static maintenance on bearings, cost, downtime, etc.
Okay, day one cost. We're becoming more competitive. Today's economy is a very competitive economy. In low voltage, 40 volt, you're going to find that we're going to be very competitive cost per kilowatt for your system. As it relates to maintenance, we are competitive on our annual maintenance events. And it depends upon if you put it in a very, very dirty environment. Go back to one of the earlier questions, we're going to probably want to see it a little more often. So maybe we'll see it twice a year. If you put it in a data center environment where it's a little more conditioned, we're only going to look at that machine once a year. So that can help you with your costs also. As it relates to bearing changes on flywheels, unlike a lot of flywheel systems out there, we're only going to do the motor generator bearing once in 20 years up to 1,999 kilowatts. As we go into the larger machines, 2,000, 2,500, 3,000 kilowatts, we'll do the bearings on that motor generator at year 11. And that bearing change would be probably $20,000. Give you an example. Now keep in mind, that's one bearing change over a 20-year life of the machine. You're not doing battery changes every 5 to 10 years or your other bearing changes every 3 to 4 years, okay? If you're using flywheel energy storage, we're gonna do the flywheel bearing change every 11 years, and it'll be a similar cost, but only once every 11 years. Hopefully that answers your question.
Yes, they said thank you. Just to add to that is the reliability issue. The battery systems, depending on the environment, batteries do fail. Depends if you have battery monitoring. If you really had non-motor loads and with a static UPS system and put all the monitoring you would need for batteries and all, the cost for a rotary is probably going to be about the same. But you have to look at your weakest link. If you're not going to have monitoring on your batteries, then you have a weak link in your system. And studies have shown that batteries and human error are number 1 and number 2 for outages. When you have kinetic energy, you can hit it multiple times and you don't have battery degradation. And also with the temperature.
To put a little extra on that for Scott, if you're not familiar, or if you are familiar with the coup de froid effect of batteries, that's what Scott's alluding to. That every time you discharge the batteries, you dig deeper into the voltage because the batteries have to start the chemical reaction and then play catch up. So they'll dip down in voltage and hopefully they don't hit the low battery voltage cutoff point. You do 2 or 3 charges, you're going to hit that low battery cutoff point, and the machine's going to actually disconnect from the load to protect the batteries for the long term. Okay. With a flywheel, unlimited discharge cycling. So you can hit it and hit it and hit it, and you'll never hit the low voltage set point that would disconnect your system. And as I said, batteries get changed in their life. My flywheels are a 25-year machine, and we can attest. I have confidence in customers all over the Eastern Seaboard, all over the world that have had machines from Pillar that are in 20 to 25-year version and are still operating. Go ahead, Scott.
There was another question, and this is a really good question because there's a lot of confusion out there. What is the main difference between with Vicon solution?
When you look at the Vicon solution, we'll start off. If you just so you guys know, Vicon has left the United States. It was acquired by a Chinese company, so they're all manufactured in China now, in Shenzhen. It's a magnetically levitated flywheel energy system. So they have a 5,000 RPM liftoff bearing to get the flywheel up to that speed where they can generate enough magnetic field to lift off the bearing and then drive to their nominal speed anywhere from 40 to 55,000 RPM. So they say that they don't have any bearing changes, which is they don't. But the problem is that if somebody comes along and shuts that flywheel off without a controlled system, and you have to have a UPS for their flywheel on top of the UPS that they're attached to for the control system. You only get 3 of those hard shutdowns is what they say, and then you get to buy a new stored energy device. And you have to take them offline twice a year for their vacuum pump oil change. So they're offline more often than we are with our system. One of the big difference with the Pillar flywheel systems is we actually have an auto greasing system. So our bearings are 100,000 year life bearings. That's how we get to 10 years. Is the auto greasing system actually perpetually improves the grease quality in the bearings real time all the time. That's why the bearings last 10 years. And also the bearings are designed to carry the full weight of the rotors so that if somebody does come off and just casually shut the flywheel off, we use magnetic levitation to lift the flywheel a little bit. So we only carry about 10% of the flywheel's weight on the bearing nominally when we're online. And if you turned it off, it settles down on the bearing and spins out in speed. But that bearing's designed to carry the weight of that flywheel for 100,000 years. So big difference in technology and what we believe is reliability. We can design ours to go completely off as well. but we need to provide a higher level of reliability because of the mission critical applications you saw me highlight at the beginning of the presentation. Hope that answers the question. Oh, also, they have two sizes. We go from 6 megajoules to 60 megajoules, which could give you 2 megawatts for a minute.
So I just want to add to that. Great answer, Bob. That when you look at Pillar's motor gen, Vicon, although it's a spinning mass, is your stored energy. So your stored energy can be battery or it can be kinetic energy with Vicon flywheel. As with Pillar, we also do have the flywheel portion kinetic energy. A lot of people will confuse motor gen with rotary.
Is that a question?
No, that was I
think it was a conclusion.
Yeah. There's a lot of great job. Thanks. So we really appreciate you guys attending, and thank you, Bob. It was a great presentation. And Sarah, thank you. Matt and Mara, thank you for allowing us to host this.
Well, thank you for your sponsorship. We really appreciate it, Bob. It's great to work with you. Wonderful presentation, and we look forward to sharing it with the rest of the community. So with that, everyone have a wonderful day.